All right, we're gonna wrap up lesson 1 finally with part 3 of this video. I know this is a long lesson, sorry guys, but this is some important stuff. So for example 9 here, we see that we are writing a polynomial function given a graph. Okay, so in previous lessons, we've learned something about in behavior, we've learned something about turning points, and so now we're gonna put that stuff together. So right off the bat, some things that I know about this graph before I start with anything is that this graph is going to be even because it goes off and has the same in behavior in both cases. I also know that it's going to be positive because it starts in the positive and ends in the positive. Let's see, what else do I know? I know that from my turning points here, there are 3 turning points, so that I know that this is going to be at least degree 4 or more. Okay, and again I got that from my last lesson. I don't know my y-intercept, but I also know my zeros. I know my zeros, and I know that at 3 I've got to be at 64. Okay, so let's do this. Let's try to make a polynomial. It says use the smallest degree possible for this thing. Okay, so a couple of things that I know. I know that this particular 0 here, since we bounce there, is even. All right, and then I know that this particular 0 here, since it goes through, is odd. And I know that this particular one, since it goes through, is also odd. All right, so if I were to just make this up and I didn't know, like if I didn't take this into consideration, this actually wouldn't be very hard of a problem. This makes it a little more difficult, but it's not bad, as you'll see. Okay, so I know that I have a 0 at -1. So I'm going to say x plus 1, right? Because -1 makes this go to 0. And I know that I have an even multiplicity here because we bounce. So I'm going to square that. Okay, then the next one is going to be at 1. So we have x minus 1 because if you plug that 1 in there, it makes that go to 0. And that has to be odd, so I'm going to keep it at 1. Okay, so I don't have to put it there because we assume it's 1. And then I have a 0 at 2. So x minus 2, and that one has to be odd as well. So I'm going to leave it like that. So if I didn't know anything else about this and I didn't know that 0.3 comma 64, I could actually just leave it like this, and then I could FOIL this out if they want the polynomial. It depends on what form they want it in. This is what it would be in factored form. But we have to make sure that it goes through 3. So to modify this to make sure that it goes through 3, I can actually just put an a out in front of this and solve for the a. How do I solve for a? That's a good question. Well, I know that my x value has to be 3. And if I get a 3, it has to equal 64. Right? So if this whole thing is equal to y, right? So if my y value is 64, okay, I need to solve for a if x is 3. So I can say 3 plus 1 here squared times 3 minus 1. I'm just plugging in my 3 for x, right? 3 minus 2, and we won't put the equals y because I have 64 over there. Okay, so let's do some simplification here. This would be the same as 64 equals a times, this would be 4 squared, which is 16, right? Times 3 minus 1 is 2, times 3 minus 1, which is, 3 minus 2, which is 1. Okay, so if I simplify that a little bit there, I get 32 times a is equal to 64. So that means my a value has to be 64 divided by 32, which is 2. So my final answer here for my polynomial in the smallest degree is this. Let me put this in, well, I'll just keep it in blue and I'll do it up here. It's 2 times x plus 1 squared times x minus 1 times x minus 2. I hope they let you leave it in factored form like this. If they don't, though, you'd have to FOIL the whole thing out. But I think this will be acceptable. All right, so that's example 9, and I think this thing walks you through it. Looks like they got the same thing as us. Perfect. And we're done with example 9. Okay, so that's how you would use a picture to make a polynomial. I'm glad they leave it in this form. So here's a little summary of what we've done on the last lesson up until what we just did. So just a couple of things to keep into consideration here. When we're graphing a polynomial, it's smooth, it's continuous, it acts like the leading power function. It has a y-intercept that is the constant term. The maximum number of turning points is whatever the leading coefficient is minus 1. So if I have x to the 6th, the maximum turns it would have would be 6 minus 1, which is 5 turning points. At a 0 of even multiplicity, the graph touches. At a 0 of odd multiplicity, the graph crosses the x-axis. Between zeros, the graph of f is either above or below the x-axis. That's a no-brainer. And then the end behavior, the graph behaves like the graph of the leading power function. Okay, so I think I already said that. Objective 4 now is to analyze the graph of a polynomial function. Okay, so example 10 says, how do we analyze the graph of a polynomial function? So here, if I see this, okay, they want us to figure out what this thing acts like. If I know that this x term is squared and this one is not, and I multiply them together, x squared times x will give me x to the 3rd. So I know that this is an odd function. It behaves like x to the 3rd, so it's something like this. Okay, I know that I have a 0 at whatever makes this go to 0. So if you don't know, you can set it to equal 0, right? So we have 4x equals 1, x is equal to 1/4. So at 1/4, the graph touches the x-axis, but it doesn't go through. Okay, so at 1/4, we have it touching, doesn't go through. And then at -3, we have another 0. 1, 2, 3, so my graph's off a little bit here. And that one does go through, so that one goes through. So at -3, we know we have a crossing. Okay, so a couple of things that, like if we're not sure about how to graph this thing, one of the things that they're teaching you to do is to just take this out of factored form so that we can find out what our intercept is. All right, so I can find out what my y-intercept is if I take it out of factored form, and it appears that it's going to be at 3. So at 3, I have this guy happening. I know that this is a positive function. So here we go. Let's put a better picture in here. So now that I know all that information, okay, at -3, we go through. At 1/4, we touch. And at +3, we have a y-intercept. Okay, so here we go. It's going to come up. We're going to go through -3. We're going to cross at 3. We're going to come back down and touch at 1/4. And then we're going to go off this way. Okay, so that's what that should look like. And I don't know that they're even going to make you graph that, but that's the picture, right? So I think that's all that we need for that one. And then for 10, it says how to analyze the graph of this guy, for example. Oh, this is example 10, my bad. So then they do a picture. Okay. And what's interesting about this picture here, they're saying to use a graphing utility. I don't know that this thing is crossing here at 3, which is interesting. But anyway, the approximate turning points of the graph, yes, you can find those. The way that you find those with the graphing utility is when you put this in, on Desmos, you can just, you can click on these points. So if you're on Desmos, you click on these points and they give you this. I don't know if they'll give them to you to the nearest 100th or to the nearest 10th, so you might have to do it on your graphing calculator if they don't give that to you accurately on Desmos. But all you do is you put it in and you use your maximum and minimum function. So use your maximum function, they have you approximate it, so you would choose a point beforehand, choose a point after, where the turning point is, and then say use the maximum feature on your calculator, and it'll give you this point. And same thing here, use the minimum, right? You choose the value before, choose the value after. They'll probably have you guess where it is, and then they'll spit out a minimum for you. Okay, so the graphing utility is actually very handy in this, because it would be very difficult to nail this, you know, without having some kind of technology. Getting this to the nearest 100th place value would take a long time. So it's a good tool to have. And then it says here how to, continuing on, step 6, use the information in steps 1 to 5 to draw a complete graph of the function by hand. And I guess it is, the scale is going by quite a bit here, so it does cross at 3, so that's good. So we go through at -3 like we said, okay? The graphing utility allows us to find out how high up we go. There's another way to figure that out, but we'll let the grapher do it. Then we know that it crosses at 3 on the y-intercept, and then we know we have a bounce at 1/4, right? And then it goes off and acts like x to the 3rd. Okay, so there's our picture. And then step 7 says find the domain and the range. Well, the domain will be all reals because we can plug in whatever we want for x. And the range will also be all reals because this goes down this way to infinity and up this way to infinity. Okay, so there's the domain and the range. And then step 8 says use the graph to determine where the function is increasing, where it is decreasing. Oh, okay, that's interesting. So it's increasing from negative infinity, I don't know why I did an 8, negative infinity all the way up to this turning point. So negative infinity to negative 1.92. I don't know if in interval notation, I don't think they include that yet because it's a turning point. And then it goes, so it's increasing here, and then it's also increasing from 0.25 to infinity. Okay, so it's increasing from this turning point to infinity as well. So those are the two places where it's increasing, and then it'll be decreasing between the turning points all the way down to here. Okay, so it's decreasing from, on the x, from negative 1.92 over to 0.25. Decreases on that interval. Okay, so in summary, there's a number of steps to analyzing this graph. We're going to determine the end behavior, find the intercepts, determine the zeros and their multiplicity to see what happens. Do they go through? Do they bounce, depending on whether they're even or odd? Then they have you use a graphing utility, which I think is kind of a cheat, but it's good for figuring out where those maximum and minimum points are so that you can figure out exactly on what interval something is increasing or decreasing. And then we approximate the turning points of the graph using that graphing utility. Use those steps to draw the complete graph, find the domain and range, and then use the graph to determine where things are increasing and where they're decreasing. Last example is this: how to use a graphing utility to analyze the graph of a polynomial function. Okay, so what they want you to do now is they want you to just graph this right off the bat. So if you put this into your grapher, okay, or you can put it into Desmos for all I care, it doesn't matter. Before you do that, but you can put it right off the bat, we know that it's going to act like x to the 3rd. So in general, it's going to do something like this. Okay, so we know that's going to happen. So it says step 1, determine the end behavior. It's going to act like the x to the 3rd, right? So it's going to act something like this. It's going to go off to negative infinity and infinity in either direction. Then step 2 is we're going to use the graphing utility to graph the function. All right, so they show a picture of it there. I'm not going to do that on this video, but you guys can figure that out in your graphers. You just put it into your y equals function. And then you can use the grapher at that point to figure out what the y-intercept is, what the max is here, what the min is here. Use your max and minimum features. You can also figure out where it crosses right here using the root. The root or the solve feature will tell you where this thing is. So that is the root feature or the solve feature when you graph this thing. And what else do we need to know? Oh, we could use a table. Yeah, you could technically use a table and get a table from the graph if you wanted to. I don't know that you would need to for this lesson, but you could. And then approximate the turning points of the graph. So again, that's just using your max or your minimum feature. And then step 6 says use the information to graph the graph by hand. So I would identify all those major things, and then on your platform for homework tonight, you're going to probably need to know exactly where this happens, and then they allow you to put in a point of where maximums and minimums happen on that thing, so that you guys can get an accurate picture. Or they might just have you match a picture that would work, right? So they might have a bunch of different drawings, and then you match the one that you get on your graph. And then you can find your domain and your range and the places where it's increasing and decreasing. Again, it's going to be important that you do that either on Desmos, which I don't know if it rounds to the nearest hundredth, or on your TIs, so that you can get these things accurately. And I'll show you guys how to do that in class. We're going to skip Objective 5, so if there's anything about building a cubic function of best fit on your homework, you can skip it. All right, guys, that's it.